Welcome to part 2 of the pre-June exam paper 1 walkthrough. So if you remember, on our last video we covered questions 1 until 4. So for this one we'll cover the remaining ones. So this will slightly be a longer one because we are covering questions 5, 6, 7, 8 and 9. Okay, so the aim is to finish the whole question paper, and then hopefully have you understand how to answer exam questions like these in general. Okay, so continuing where we left off, we're off to start with question 5. So here we have a small block of mass 0.4 kilograms that is released from rest. Okay, so you can come and mark this right here. So it is released from rest at point, let's use rate, so at point A, right? We note that means at point A, we can even call it VA if we want. Oh, let me use red instead. VA is 0 meters per second. Right, so the initial velocity, so my VA just means that the velocity at point A, VI can be equals to VA if my point A is where I consider to be my initial point. Okay, so it depends. So it can be my initial velocity, but for now let's call it VA. We'll see when we start calculating if we need to call it VI and so on. All right, so this point is 0.8 meters vertically above the ground. As you can see, 0.8 is there. So now it takes the block 3 seconds, right, to slide from point A until point E. So this whole slope, or this whole path from point A to E, it takes the block about 3 seconds to complete that whole thing. So that means, so now we are also told that it slides down from point A, B, C, D, all the way up until E. So when it reaches point E, it comes to rest at point E, right? It comes to rest. Okay, so that means the velocity at E as well, let's call it VE, would have to be 0 meters per second. The keyword there is rest. So at point E, it's at rest. Okay, so the length of the track from A to E is 8.1 meters. Okay, that's not given in the diagram, but the length of the track from A to E is 8.1 meters. So that is the total distance. That's the total distance. So we have the total time, which was this one, and now we have the total distance, which is this one. So if you remember, in grade 10 we would calculate the average velocity using the total distance and the total time, right? So that's one thing you must note there. Point D is 0.3 meters vertically above the ground. The surface of points A to D is frictionless. Okay, so this whole part A, B, C, D, there's no friction there. Okay, so we are not expecting any friction here, there, and there. That means if there is no friction, we can usually use our energy principles to find whatever physical quantities that we need at these points, right? We can use laws of conservation. We can use the law of conservation of energy, which is the law of conservation of mechanical energy, for instance, right? Because there's no friction there, and then you can be able to find whatever physical quantity that you would need at point A, B, C, and D. Because why? There's no friction across those points. Okay, now we are told to also ignore the effects of air resistance. Okay, there's no additional information that is mentioned. All right, so let's continue to our first question in this question 5. So we come here. The first question is, state the principle of conservation of mechanical energy. So once again, just to emphasize these type of questions, your definitions and stating the principles or laws, they account for about, I think it's 13% of your total question paper, the max. So you must make sure you know all of your definitions. For instance, if you're going to write a paper 1, you must know all the definitions and laws associated with all the chapters that are in that paper, right? Of course, you might forget a few of those, but try to know all of them, especially the ones that are usually used the most, like your law, Newton's law, principle of conservation of mechanical energy, what's this, frictional force, and so on and so forth. All right, all those type of definitions, you must know them. You must know them off by heart, and then you'll be able to get an easy 13% in that paper, or you are more likely to get the whole 13%. All right, so 5.1, we are asked to state the principle of conservation of mechanical energy. So the idea of this principle is that in an isolated system, which is there's no friction there, there's no air resistance, and there are no other external forces affecting that system, the total mechanical energy will be conserved, right? Remember, mechanical energy is just the sum of the potential and the kinetic energy of an object at a particular point in time, right? So at a particular point in its motion or during in a path. Okay, so now how you state it is you would say the total, and this is the easiest way to state it, by the way, the total mechanical energy in an isolated system remains constant. That's all. The total mechanical energy in an isolated system remains constant. So that's all you'd have to say in terms of stating this force. Then let's go to 5.2. Is the kinetic energy at point B the same as that at point C? Right? Only yes or no. 5.2. Okay, so the kinetic energy at point B, is it the same as the one at point C? A simple answer would be yes. But then why is this the case? Right, remember, once now, there are two ways to think about it. When this object is at point B and it's approaching point C, there is no friction here. So this object is not affected by friction. There's also no air resistance, and which means it's an isolated system, basically. So if it's an isolated system, there's nothing slowing down the block in essence. So the velocity here at B will be the same as the velocity there at D, because friction is not slowing down the block, which usually is what slows down objects. And then also the air friction is also not slowing down the block. So yes, we can say the kinetic energy at point B and C will be the same. And then another way to think about it will be, if you check, since this path, the one that we have highlighted, A, B, C, and D, this whole path, it's frictionless, there's no air resistance. So there's no air resistance obviously for the whole path until E, but there's also no air resistance for A, B, C, and D. For A, B, C, and D, there's both no air resistance, and what else is there? No friction. The surface is frictionless, right? So now it means it's an isolated system. Of course, we've already established that. So what happens then is, if I move from A to B, my mechanical energy should be the same between these 2 points. So if I take the mechanical energy at A and the mechanical energy at B, I should get the same value. So if you notice, at A, velocity is 0, right? So the mechanical energy there, it's mainly just mgh, which is the potential energy, because if you remember, let's say this is mechanical energy, you take your kinetic energy plus your potential energy, right? So since velocity is 0, this whole term will go out. So at point A, you only have the potential energy contributing to the mechanical energy, to the total mechanical energy. And then when you get to point B, the height now, so this is for A. If you go to point B, this is just a side note. The height now is 0, and then we have a velocity plus mgh. The velocity will be non-zero by the time you get to point B, of course, because the block would have accelerated to some speed. So now, but the height is 0. So the total mechanical energy only includes kinetic energy. Let's go to C. Em, let's call it C. At point C, we do the same thing, half mv squared plus mgh. I'm just proving you that mechanical energy between, kinetic energy between C and D will be the same. So at point C, mgh, the height is still 0, so you're only left with the kinetic energy. So since the speed will be the same, you will see that the kinetic energy will definitely also be the same. So that's another way of thinking about it. So yes, that's what happens at those points. Okay, let me erase this. So if you say EMB is equals to EMC, you will find that at B, the only thing that's there is the kinetic energy, and at C, the only thing that's also there is the kinetic energy. So you see that the kinetic energy at B is the same as the kinetic energy at C. That's another way of looking at it, okay? All right. So our answer is yes, and then for 5.3, we have to give a reason for our answer. The simple reason is that the surface is frictionless, or this is an isolated system at B to C. Okay. 5.2. 5.2, I'll write yes. Our what's this? The kinetic energy is the same. Then 5.3, we write our reason. Give a reason. The surface is frictionless. Yeah, let's leave it as that. The surface is frictionless at point A to B to C. Okay, so that's what you would typically say. All right, so if you want, you can continue and say, well, which is basically everything I explained. The surface, yes, is frictional at points B to C. And then since these 2 points are at the same height, their gravitational potential energies will be equal, which is 0 in that case. Then, therefore, their kinetic energies would also be equal as a result. Right, so yes. So we can say Yes, I'm trying to make it shorter, okay? Because alternatively we could say, well, the points B to C are frictionless and these points are at the same height, and then since mechanical energy is conserved, they are okay. I'm making the explanation a bit longer so that you can sort of take notes, but the gist of it is that the surface is frictionless. Yes, I probably didn't need to add that. And these points are at the same height with their potential energy equal to 0. So since mechanical energy must be conserved, their kinetic energy will thus be equal. So there's probably a shorter way of putting that since this is just a 1-mark question. So since, let me just drag it, it's fine. You will find a shorter way, but this is the idea, okay? Is conserved You probably don't need a paragraph this long to explain a 1-mark question, but the whole idea is here. Okay, so alternatively, you could have said the points B and C are at the same height, potential energy is 0, and then since mechanical energy is conserved, the kinetic energy at points B and C will be the same. So this is a more elaborate explanation, but you don't need to drag it this long. This is for you to just take notes. In an event where you can't really summarize it to one simple sentence, you can write the whole thing and get one mark. Still fine. The aim is to be correct. Okay. Now, let's go to 5.4. State in words the work energy theorem. So that's 5.4. Remember, the work energy theorem says in formula form that the net work done, the work done is equals to the change in kinetic energy. That's basically the work energy theorem. So if obviously they hadn't stipulated that we must state it in word form, we would use just a formula and this would be enough. But it has been stipulated that you must state it in word form. So in words, you would simply say the work done. So the work done on an object by a net force, okay, is equal to the change in the object's kinetic energy. That's enough. So, okay, that's it for the definition. The work done on an object by a net force is equal to the object's change in kinetic energy. There's another way of saying it, but you would be saying the same thing, just paraphrasing, okay? Now, 5.5, use the energy principles to calculate the speed of the block as it reaches point D. Okay. We are at 5.5. So energy principles include the principle of conservation of mechanical energy, or the work energy theorem, and so on. Okay, so let's see. Let's see what we know about points A and D. So what are we trying to find? We're trying to find the speed of the block as it reaches point D. All right, so what do we know about A and D? We know that the velocity at A is 0 meters per second, which means the kinetic energy at that point should also be 0, okay, because the velocity is 0. And then, but the potential energy of the block is not 0. We'll use this height to find it. And then when we get to point D, that's where we're trying to find our speed at point D, or the velocity, right? Speed and velocity are not the same thing, but we'll use V, obviously. So now at point D, we are trying to find that. We know the heights, so this height can help us calculate the potential energy. So what we are getting to here, we know that the sum, or the total mechanical energy at A, is equal to the total mechanical energy at D. D is the last point on the frictionless surface, so we can use it. Okay, we can use point D. It's just before you start that path DE. So path DE has a lot of friction, so we wouldn't really use energy principles to find anything in path DE. Okay, so let's do that using energy principles. So we can say that the total mechanical energy at point A is equal to the total mechanical energy at point B. So we can say half mv squared plus mgh at point A is the same as half mv squared plus potential energy at B. So obviously this is just a third step to some people. Some people want to come to the second step and write that the kinetic energy at A plus the kinetic energy, no, not kinetic, the potential energy at A is the same as the kinetic energy at B plus the potential energy at B. So some people prefer writing it like that. So you can still do it like that. It's not an issue. So now at point A, you can substitute if you want, but I would simply write a 0. You can substitute the 0 and the mass and so on. We have 0.4, which is the mass of the block. Where is it? It's this guy here. That's the mass of the block. All right, so that's our mass. And then our velocity at A, remember we said it's 0, so that's 0 squared. mgh, mass, is still 0.4, 9.8 times our height at A, I think it's 0.8. Let's go check. Height at A is 0.8 meters, okay? Then height at D is 0.3, okay? We'll remember that. Now let's go to B. B, oh, this is a mistake. We are taking A and D, sorry. Not A and B. I'm used to just points A and B. A and D. Sorry for the confusion. So we are taking points, this one and that one. Let me highlight them for you. Points A and D. We are interested in those two, okay? So that's what the question wants, points A and D. So it wants the velocity or the speed at point D. All right, so let's do it. Not 0.4. We don't know the speed, so we can leave it as v squared plus m, still the same block, right? 9.8 times, what's this, h is 0.3. okay, all right. So from here it's just substitution, solving, and transposing, the basic stuff you would do mathematically. So for this one, it'll obviously go to 0. This will go to 0, and then we'll be left with that one. So that's 0.4 times 9.8 times 0.8. We get 3.136. is equals to 0.2 v squared plus 0.4 times 9.8 times 0.3. okay, that's 1.176. so v squared, I mean speed, is simply the square root, you would put it in your calculator, of 3.136 minus 1.176, all of this over 0.2. So I just combined it to one step. So basically step 1, I took this, I transposed it to the other side, right? After transposing that, I divided both sides by 0.2, so get rid of the 0.2 on the right hand side of the equal sign. After doing that, I then took a square root of both sides, both the v and whatever will be on the left hand side, and then my result was this one. Right, so you can take it step by step, but in this video I'll just jump all those steps to this final one. Right, so our answer would be I get 3.13 meters per second. Okay, so that's it. That's how you would get your 4 marks there. So let's call it EM at point A is the same as EM at point D. Forgive my notation, but yeah, this is how I would answer. Total mechanical energy at point A is the same as the total mechanical energy at point B. All right, so now 5.6, the distance between D and E is 3 meters. Okay, so we're being told now something new. This was not there initially. They are telling us that this distance is 3 meters long. Okay, so use energy principles to calculate the magnitude of the frictional force acting on the block between point D and E. So once obviously there's a force involved, you have to use the work energy theorem if they tell you to use energy principles. Okay, so you cannot use the conservation of mechanical energy. First of all, the path won't allow you to use that because there's friction in that path, so energy won't really, let's do this, be conserved. All right, so just before I write 5.6, let me go back here just to clarify something I said earlier. So if you remember, I said we cannot use energy principles when the path is there's friction on the path. Okay, so by that I meant this principle. All right, so because remember, energy principles include the principle of conservation of mechanical energy and also the work energy theorem. So you cannot use the principle of conservation of mechanical energy for the simple reason that it is for only when there are conservative forces that are present. And remember, once there's friction is not really a conservative force, so you can't use mechanical energy. It won't be conserved per se. Right, so once friction is present, mechanical energy won't be conserved. So now you must look into using the work energy theorem. So that's one thing I wanted to clarify. And then secondly, in this case, we are able to use the work energy theorem in case you forget when to use the two. In this case, which is 5.6, we are able to use the work energy theorem because we cannot include forces in the principle of conservation of mechanical energy. So we know that since they are telling us to use energy principles, we can lean on the work energy theorem because it allows us to include forces in it. Okay, so that's one thing that you can also note for this particular question. Right, so that's one clarification I wanted to make there. And then, so in short, you can use principles of energy principles in both friction and non-friction surfaces or environments or paths, right? Because it can be air, it can be a surface and so on. But you must be careful. For principle of conservation of mechanical energy, it only works when there's no air resistance and there's no friction as well. And then work energy theorem works pretty much everywhere. Okay, so that's it. Okay, so those are the limitations of the conservation of mechanical energy. Now let's go to our question 5.6. The distance between D and E is 3 meters. Use energy principles to calculate the magnitude of the frictional force acting on the block between point D and E. All right. So from points D to E, if you draw your block, say this is our block, right? The only force acting on it is our kinetic friction. Okay, so remember, our kinetic friction will act on this block until it comes to a halt, and this block will travel about 3 meters, right, until it gets to a point somewhere here. Right, until it gets to a point somewhere here where now its velocity is 0. Okay, so that's one thing you must understand. So now if you remember, this will be our delta x, and if you remember, a force applied on an object, or the net force applied on an object for a certain amount of distance, will do work on that object. So if we say Fk times the 3 meters times now the cosine of the direction of the force, we can get our work done by that force, right? If you remember, we said work done by a force, we can say it's the net force times the cosine. Okay, and obviously the cosine depends on, it's the angle between the force and the path or the direction. Okay, all right, so if you check friction, the path direction is that side and frictional force is going that other side. Okay, so if we measure the angle between the path, which is this one, and friction, you'll find that this theta is 180 degrees. So we must use cos 180 V. So that's what the theta represents. Okay, so let me just label them for you. That's friction, that's the direction of motion or the path. Let's call it delta x actually. Yeah, so delta x or displacement is in that direction, is to the right. right? While friction is to the left. So the angle now becomes 180. So that's how you get theta, okay? Now let's continue. So if I do that, it means I know that this is the same as change in kinetic energy. All right. So what I can do is, let me break it down for you. Actually, let's take this whole thing that side. So if I come here, let's say I come here, you might start by saying the net work done is equals to change in kinetic energy. This is the work energy theorem, right? And then now you come and you say the network is F net times delta X times cos theta is equals to delta K, right? But in this case, there aren't many other forces, so you can just put our F here. Don't need to say much. So F times delta X times cos theta. Then from here you can start substituting. But do we know our frictional force? That's the question now. We can find friction. We are not told what it is here. We know that friction is N times delta X times cos theta. So this N will be simply mg. Sorry, I'm breaking every step so that you can see before I substitute. Okay, so you don't need to write all of these steps, I'm just showing you. So from here I think I can say half mvf squared minus half mvi squared. Then here I'm just buying time for my left hand side equation, if you get what I mean. I could have substituted a long time ago, but I want to show you a breakdown, everything. Okay, so now we have that. Now we can start substituting values. 0.4 is our mass, 9.8 is our, what's this, is our gravitational acceleration. Delta X, we are told that it's 3 meters. And then we get cos of 180 degrees. And then we get 1 over 2, 0 squared minus the initial one. We found it here, remember? At some point they asked us to find the speed at d. So we already have it. So our initial speed now would be 3.1, what was it, 3.13, which is the speed we found for d, right? This is vd. So for the situation we are considering now, vd, which is this whole thing, because now we are just basically looking at this part of the equation, this one. So now for that one, we have VI being 3.13 meters per second and VF, which is VE, being 0 meters per second, right? And then our displacement, which is 3 meters, okay? Now, let's do that. So VI is 3.13 squared. Must be careful there. So now you don't have to factorize like I did. I was just sort of buying time, if you get what I mean. You can just substitute the way it is here. Okay, you don't have to factorize anything. So now our left hand side, we will get 0.4 times 9.8 times 3 times cos 180. That will give us minus 11.76. Okay, Then on the other hand, 0.5 times 3.1. You must be careful here. So it's easy to take 3.13 and make it VF, but that's just a mistake. So be very careful when you substitute your VI and VF. Remember, we said the final velocity will be 0 because this thing will come to rest when it reaches point E. Okay, so VF has to be 0. VI is point D where it started. Okay, so 0.5. So here I get minus 4.90. I will round off, not really supposed to. So now I left something out here. Sorry, what have we done? Oh, I'm calculating friction on both sides. That's a weird mistake. Sorry, I was not supposed to do that. That's a rookie mistake. I lost my ways. We can fix that, it's not an issue. So in my mind, I was calculating the velocity of point E, which is weird because it's 0. And we are told specifically to calculate force F. Okay. All right, so let us continue. So apologies for that. F is our friction now. Okay, so we can substitute Fk here. I don't know what I thought I was doing calculating, and now both sides have values. I'll have 11.76 equals to whatever was on the other side. Okay, so that happens. Okay, some weird mistakes like that happen. All right, now so what we can do, we can substitute that, cos still 180 here. So you don't always have to, some people prefer substituting at the end. So what that means is they would have made F subject of the formula and then they substitute at the end. Okay, in fact, let's make this our fourth step. So we will have 0.4. So I can move this to become our fourth step. What I mean by that, let me show you. I'll have Fk times delta x times cos theta. That's our step 3. And then now I'm expanding our delta k, which is 1 over 2 mvf squared minus then that's our third step. Vf is 0 minus 1 over 2. You substitute again. You can factorize if you want, it's up to you. Vi, we calculated it as 3.13 squared. Okay, that's fine. So from here onwards, we can start solving. 3 times cos 180. That should be minus 3 actually. Doesn't need a calculate. Minus 3 times Fk is equals to, you can even write it as minus 3 times Fk is equals to 0.4 minus 5 so let's say 88. Then Fk, you divide both sides by minus 3, and you get 1.96 newtons. So this is how you would find the force. All right. So yeah, everything I've explained until I made that weird mistake on that calculation is fine. Okay, so the diagrams, how to find theta and so on, everything was fine. I just lost it in the calculations there, but we're back. And yes, this is how you would find, or you would answer question 5. Okay, let's see on the next one. Oh, it's continuing. There's 5.7. This was quite a long question. Let's check out 5.7. All right, so this is our question 5.7. Let's move. So we have a motor. So this motor pulls a heavy crate of mass 500 kilograms with a constant force by means of a light inextensible string. Okay, so we have the mass, constant force, okay, light inextensible string over a light frictionless pulley. Okay, the coefficient of kinetic friction between the crate and the surface is, so this surface is not frictionless, it has friction. Okay, so remember what I always say, you come here, you annotate. We don't really care about the motor, they didn't give us anything about it, but there's tension here, right? There's tension here, T, right? Then we have our normal force, N. Then there's weight, which is always acting downwards. Then of course there's our frictional force, which is opposing the direction of motion. This is our kinetic friction. All right, so those are the things that we have so far in our force. Let's call this our force diagram. All right, so from here, remember what I say, you can obviously draw now a free body diagram for yourself. You know that you would have the normal force, you would have the weight, you would then have your friction, then you have your tension. Since this block is moving upwards, it means it has overcome tension. So usually I draw the vector, the tension vector, to be a bit longer than the frictional vector in cases like this, because I know that whatever force is being used to pull the block is greater than the kinetic friction. So I can represent that in my diagram as well. All right, so now remember, weight will have to have its component. So let's try and get these components. Remember, we would have a parallel component. Some people call it weight parallel, like this. I don't like those symbols, so I usually use y. Sorry, this is x because it's in the x-axis. So that's my x component of the weight. And then for the perpendicular component, I use y. So I would say wy. And obviously, the angle is always between the perpendicular component and the actual weight vector, like this. So I put it there, right? It's not visible, but it should be here. That's our 30 degrees, okay? So yes, we are done resolving and we are done annotating our diagram. Okay, so we can start answering the questions because we've interpreted the question, we've interpreted the situation. All right, so define the term power in words, right? If you remember, power is the rate at which work is done. That's it. That's the simplest definition of power that even the formula tells you. You can say P, something like this. It's the rate at which work is done. So did they specify, or they said in words? If they didn't specify, you could have written it like this and left it here, right? But they said in words. So power is the rate That's it. That's how you define power, the rate at which work is done, or the rate at which energy is expended. It depends which one you prefer, okay? But the rate at which work is done, I prefer that one because it's easy to remember from the formula itself. Draw a labeled free body diagram of the crate while moving on the incline. We've already done that. And remember what we said, if it has 4 marks, it means your free body diagram ought to have 4 forces as well. So it must have 4 forces. If this thing has 4 marks, it means your free body diagram must also have 4 forces in it. If it has 3, then you know that there's something missing there. It's not complete. So you can just take the one that we already did and I'll paste it there. Okay. That is our free body diagram. Okay. Right. Now, let's continue. So, we go to 5.7.3. Write down the name of the conservative force acting on the crate. Remember, they are what we call conservative forces and non-conservative forces. Conservative forces, they are dependent on the path taken by the object, while non-conservative forces are independent of the path taken by the object. So what we, for example, a conservative force, it's the other way around, my bad. A conservative force is independent of the path taken. For example, if we're talking about gravity doesn't care whether the path has friction or no friction. Gravity will always be there. So it's independent on the path taken. That's what it means. If the path has friction or no friction, or if it has whatever is there, gravity doesn't care. It will always be there. Alright, so even electrostatic forces as well, if you have 2 charged spheres or 2 charged particles, electrostatic forces will be there. They don't care whether or not in that space there's friction or there's no friction. It doesn't matter. The nature of the force is not really affected by that. And the non-conservative force is a force for which the work done in moving an object between 2 points will depends on the path taken. So example of that is obviously, the obvious one is frictional force. So frictional force, it can only exist if the path allows it to be there. So if we are moving on a rough path, there will be friction. But if the path is smooth, there will be no friction. So you see, friction depends on the type of path that is being taken by that object. Okay, so that's one thing. So in this case, we're asked for a conservative force. So it's a force that is independent of the path taken, that is acting on the crate. The simplest answer you can go for is weight. Is there any other force that's independent of the path taken? You can think about that one, but the easiest one to go for is your weight, your gravitational force. Am I on 5.7.3. All right. The crate moves up the incline at constant speed of 1.5 meters per second. Okay, constant speed. It means acceleration is 0, right? Remember that one. Now we're asked to calculate the average, keyword is average power delivered by the motor while pulling the crate up the incline. So this is 5 marks. Okay, so let us start. All right, so if you notice, we've been given, we know the following: acceleration is 0, right? And then velocity is 1.5, or speed, sorry, is 1.5 meters per second. So now, for us to find the average power, remember, average power, if there's a constant force being applied, we take that force we multiply it by the velocity at which that object is moving. Then we can know that whatever object is applying the force is delivering a power of a certain magnitude, right? Which is a product of the force applied and the velocity at which that object is moving. So in this case, we have a motor. The motor is the one applying a force on the 500 kilogram block. As a result of the motor doing that, the block moves at a constant speed of 1.5 meters per second. So now we need to understand how much force does the motor apply on the block, and then we will take that force and multiply it by the velocity of the speed of the block, which is 1.5 meters per second. Right. So to do that, we must first find our force, because speed is already given. Okay, so let's find the force that the motor applies. So when it comes to the motor, the force that it's applying is actually the tension in the string. Okay, so if we can find T, we would know that that's our force that the motor is applying, and therefore we would take that tension force and multiply it by the speed of the crate, and thereby we will be able to find the average power that this motor delivers. Okay, so in your formula sheet you would find this formula as well. Let's check. So it should be somewhere here. Right, there it is. So if you check, we know that the average power delivered, it even says PAV, is equals to the force times the average speed. Okay, so that's what we're looking at right now. All right, so it's not a formula I just found from nowhere, it's even in your formula sheet. Okay, so let's go about it. You can take it as it is if you want and say P AV, but we'll use it later, not now, is equals to the force times the average velocity. So obviously the first step is let's find T. How do we find T? So we know that if we use Newton's second law, we can find T, because we can say F net is equals to MA. We already know that A is 0, so this whole right hand side of the equation will be equals to 0. The only unknown on the left hand side of the equation will be T. Why? Because we can find Fk, we can find the parallel component of weight, and therefore we can just find T. Alright, so some people prefer to find these individually and then substitute once. So what I mean by that, they'd first calculate Fk and then calculate the parallel component of the weight, and then from there they use Newton's second law to find T. You can either do it like that or simply substitute in the formula. So for the sake of making sure that everybody understands, we'll do it step by step. We will break it down. So let's start by finding Fk. Right, we know that Fk is our kinetic friction, is equal to mu k, the coefficient of kinetic friction, times N. N is our normal force. So N in this case, it's equals to our perpendicular component of weight. So that's mg cos 30. Okay. So we can actually start by finding N. N is equals to mg cos 30 degrees. So our mass, we are told that it's 500 kilograms. So because I will round off a lot in my steps, the final answer might differ for someone who just take all of this and substitute it as it is in a one step by using F net is equals to MA. So our 30. So 500 times 9.81. Okay, let's use 9.8. That's the high school one. 9.8 times cos 30. This would give you 4,243.52 newtons. Okay, that's the first thing. We find our normal force. Okay, we have our normal force. Now we want to find our friction. Let's just say calculate. You don't have to label your steps like this. I'm doing it so that you can take a mental note. So for Fk, we know that Fk is equals to mu k times the normal force. So we already know that mu k is 0.15, and we just found the normal force to be 4,243, right? All right, so 0.15, I get 636. So from my calculator, I just saved the answer and multiplied by 0.15. 636.53 newtons. Okay, so I have that. Now what else do I need? Now I need to find my Wx. These are all the forces that will be involved in my equation when I start saying F net is equals to MA. So Wx, which is my parallel component of the weight, is simply mg sine 30 degrees, which is the 500 times 9.8 times sine 30 degrees. And I get 2,450 newtons. All right, so now I have pretty much all the forces except tension, of course, because I don't know it. So what I can do, right, these are all my forces, the ones I'm interested in. I don't care about this one, and that one. I can use those two. What else is there? Okay, nothing else. All right, so from here I can pretty much say, taking upwards as positive, I can say F net is equals to MA, right? So F net, I take my tension. Remember, I have tension pointing up, this force, minus Fk minus Wx. So plus my Fk is negative, plus my Wx is negative. Why are they negative? They are opposites to the direction that I took as being my positive. Okay, from here I can start substituting. T minus Fk. I found Fk to be 636.53 minus 2,540 is equals to 500. We said our acceleration is 0. Why? Because this thing is moving at a constant velocity. If something is moving at a constant velocity, there's not the rate of change of velocity is 0, which is our acceleration. If something is constant, it means it's not changing. So T so this is plus 636.53. T is therefore equals to 3,086.53 newtons. So that's our tension. This is our force for our equation P. This is the force we've been looking for, this one. So now we can find our average power. So all of these steps that I did, what you can do, you would have summarized them in one equation, this F net equation. So when you go to Fk, you are going to calculate tension at that point here by substituting all the values for tension. Okay, so what that means is for tension, you are going to have T minus mu k times N, which is mg cos 30, right, minus Wx, which is mg sine 30, is equals to ma. So had you not done all of these steps that we just did up here, you would have just done it in this one equation, and then you start substituting your values. Okay, so that's another way for people that prefer faster, less time, less space consuming calculations, but you would get the same marks anyway. Okay, so let's continue. Let us continue. Now we are going to find our power, our average power, P average. So now we can say this is equals to T times the, and then this is the 3086, we just calculated it. All of this times our 1.5, which is our constant velocity. When I do that, I get 4,000. Okay, this is not money, so I don't need to separate. 4,629.80 watts. Okay, so if you want to write it in kilowatts, you simply divide this by 1,000 and you'll get something like 4.63. It's an estimated 4.63 kilowatts. Still the same thing. Okay, all right, so that is what you would do. Yes, it's 4.63 kilowatts. All right, so that's how you would answer this particular question. That's our answer right there. Even if you left it here, still fine. Okay, they didn't say they wanted in kilowatts. I'm just showing you how you would have got it in kilowatts. Okay, let's continue. All right, now we are going to question 6. All right, question 6. A siren of a stationary train emits sound waves of a constant frequency of 780 hertz. Okay, that's our frequency of the sound wave. It's emitted by the stationary train. Okay, our stationary source is the train. A person in a car with a detector accelerates constantly. Okay, there's constant acceleration here. From where? From rest. So VI is 0 and acceleration is 0. Now at point X, okay, towards the train, take the speed of sound in air as 340 meters per second. So what do we have here? We have a lot of information actually. We have that, we can come annotate here. VI for this guy is 0 meters per second, and then we have that V car, actually let's call it VCI. Yeah, the velocity of the car is 0 meters per second initially. Acceleration of the car will be 0 for the whole trip. What else do we know? We know the frequency of the wave, which is the sound wave, is 780 hertz. We know the speed of the sound wave is 340 meters per second. All right, that's the speed of the sound wave. All right, so 6.1, name the phenomenon that was observed by the listener. So this listener carries a sound, he carries a detector, right? If he's carrying a detector and is measuring the sound waves emitted by the stationary train, suffice to say, the phenomenon that he will observe will be our famous Doppler effect. They were not really specific as to what exactly he's observing, but this is about the Doppler effect. Okay, so 6.2, calculate the wavelength emitted, the wavelength of the emitted sound waves. So this one, if you remember, we know that the speed of a sound wave is equals to its frequency times its wavelength, right? So it's frequency times lambda, f times lambda. But now we're looking for wavelength, so we can say wavelength is simply the speed of the wave divided by frequency, and this gives us 340 divided by 780. What do we get there? 340 divided by 780, we get a wavelength of 0.45 meters, 44 meters on my calculator. Right, so you can punch this on a calculator as well and check what you get, but I get 0.44 meters, so wavelength is in meters. All right, so now explain why the observed frequency is higher than the emitted frequency. Okay. All right, so for 6.3, we are asked, explain why the observed frequency is higher than the emitted frequency, right? So the reason for that is, remember, frequency is simply, it's a measure of how many wave fronts can pass at a specific point per second, right? So if the observer was stationary, remember the rule says this is the emitted frequency, right? Let me remove this. Picture this. The distance between these wave fronts, by the way, is the same, which is our the distance between the crests would be our wavelength. Okay, so it's the same. Now, if the source was stationary and the source is at a specific point here, stationary, right? These wave fronts that are emitted by the train would pass at that point at the same rate, right? Because the source is stationary, it's not moving. So think of the source as a door. If the source was stationary, of course, think of it as a door. It is busy swallowing these wave fronts. And since this door is not moving, the rate at which it swallows the wave fronts will be constant. It's just the same. It won't be higher than the rate at which the wave fronts get there. So that's what will happen. So as the wave fronts are approaching this door and this door is swallowing them, the speed at which they pass at this particular point where the door is located will be the same as the original speed of these wave fronts. So that means the frequency observed would be the same if the observer was constant. But now the issue is the observer is moving. So that means when the observer starts moving, the wave fronts that are passing per second through the observer will be higher. Why? Because compared to how fast they are moving when they are emitted by the source, they are also swallowed faster by this door that we have created here. I know I'm making an example of a door, right? So what that does is it increases the frequency of the observed frequency of the wave fronts, because what it effectively means, using our examples, it means right now, compared to how many wave fronts are being emitted, I'm actually taking a bit more, right, per time. So if the wave fronts, let's say 3 pass, when I was stationary, it took 3 wave fronts to pass per second, right? When I start moving, obviously I'll take more wave fronts per second, right? I'll probably take 6 or 8, but a bit more than 3, because now I'm moving, right? So there's more wave fronts that I'm able to take than when I'm stationary. When I'm stationary, I have to wait for them to pass at their own pace. But once I start moving as the observer, I take in a bit more, right? So that's how the observed frequency works. So put in simple terms, we would say that the reason that the observer observes a higher frequency is because as the observer moves towards the source, they encounter more wave fronts per second. And remember, more wave fronts per second means a higher frequency. So this causes the observed frequency to be higher than the emitted frequency. Another way in which you can put it, is you can say that the car is moving towards the stationary train, which is the source. So the observer is moving towards the source. This decreases the distance, right, between the successive wave fronts. Okay, so effectively shortening the wavelength, if you can think of it like that, and therefore increasing the frequency detected by the observer. Okay, so I'm saying the same thing but in different ways. So let me write the shortest one possible, because this is 2 marks. So this is 6.3. Okay, so we are saying the observer is moving towards the source, which is our car, right? Is moving so yes, this is how we would answer that question. So as the observer moves towards the source and it encounters more wave fronts per second compared to the ones to the rate at which they are emitted, of course, and then causing the observed frequency to be higher than the emitted frequency. Now 6.4, at point Y, which is 83.1 meters, 11 meters from point X, the person in the car measures an observed frequency of 850 hertz, right? So 6.4.1, that's where the question starts. That's where we're required to answer, actually. Calculate the speed of the car at point Y. So by the time it reaches point Y, the observed frequency measured by the car or at the car is 850 hertz, okay? And then it has covered a distance of 83.11 meters from point X. All right. So we know the frequency of the listener, which is the observer, right? Usually we use FL to say frequency of the listener or observer. We are told it's 850 hertz, right? What else do we know? We know the speed of the wave speed, which is 340 meters per second. What else do we know? We know the frequency of the emitted frequency, right? The frequency of the source, Fs. We said it's 780. We are told it's 780 hertz. All right, so once we have that piece of information, now what we need to understand is when we use our Doppler effect equation, we must know who's stationary and who's moving. So in this case, the source is stationary and the observer is moving towards the source. So how we structure our equation depends on that. So first of all, of course, before you write the equation that you'll use to calculate, you start with the original Doppler effect equation, which is V is equals to V plus or minus. That V is my wave speed, of course, plus or minus VL. Is it VL? This thing. VL. Okay, yes. Much better. So that's the velocity of the listener, and then divided by V plus or minus velocity of the source times all of this multiplied by the frequency of the source, or frequency emitted at the source. Okay, so now this is what we have. So because now we are concerned with the source moving towards a the listener moving towards a stationary source, what we then opt to do is our equation will become FL is V plus VL, because the source is stationary but the excuse me, the listener is moving. So the velocity of the source will be 0, of course, so this will go away, it will be 0. So we'll have only V remaining at the bottom, which is the velocity of the sound wave. Then we have multiply all of this by Fs. So from here onwards, we can start substituting. So you have two options. It's either you substitute at this point, or you can make whatever you want to find, which is VL in this case, subject of the formula. So let's just substitute. FL, frequency of the listener, we are told it's 850. Yes, 850. And then the velocity is 340. Wave speed is 340. I keep saying velocity, but it's wave speed. And then the speed of the observer is what we're trying to determine. And then the wave speed again is 340. And we multiply all of this by 780. Okay, you can even put it like this, it's up to you. Now from here, it's just simply mathematics. So you can say 850 just as a shortcut, 340, right? 850 divided by not divide, this is cross multiplying now, times 340, right? And then you can divide this by 780. And then you can subtract 340. I just did all these steps in one step. Then this will give you your VL. It's all mathematics. So the reason I'm taking shortcuts when I get to this part, because it's just mathematics. If you need to break the steps down, you can, but there's usually no mark for this part. So they will want the original formula, this substitution, and your final answer. Let's see how many marks this is. It's 5. Okay, so that's usually how it works. Okay, so but if you want to break it down, okay, let's just do it. I don't want to confuse others. Here you know that this is over 1, so you can start by dividing both sides by 780. Right, so you divide both sides by 780, then this cancels that. Now you have 850 if you want over 780 is equals to 340 plus VL over 340. Let me change it so that then from here you can cross multiply, and then you have 340. In fact, you don't have to cross multiply both sides, you just take the 340 that side. 340 times 850 over 780 is equals to 340 plus VL, right? So the nicest thing about cross multiplying, you don't have to always exchange the numerator and denominators. You can just take one the other side, which means I could have multiplied by 340 over 1 and then 340 over 1. The reason I'm doing that is to get rid of this 340. Okay, right. So once you've done that, you can then now take the 340 that side, so it becomes minus 340. So that's how I got to that equation that I had before. So that VL will simply be, I'll write the answer here. So 340 850 over 780 minus 340. Your answer should be I get 30.51 meters per second. So that's how you would find the velocity of the observer, right, in this particular case, 30.51. All right, so that's Doppler effect for you. Now let's go to acceleration of the car. Ooh, we made a huge mistake here. We said VI is 0 meters per second, and then A is 0 meters per second squared. All right, so we are told that it accelerates constantly. So that means A is equal to some value made, let's call it C, in meters per second squared. So now we are required to find what that value is. So it's not necessarily 0. It would be 0 if they said this thing moves at constant velocity after it starts from rest, which is how I interpreted the question, but that's not true. So from rest, it accelerates constantly. I even underlined there, which means our acceleration does not change, right? From rest, it accelerates constantly. So it's like if you've ever seen when in free fall, an object will always accelerate constantly at 9.81 square meters per second. Okay, no, at 9.81 meters per square second. Okay, so that's due to gravity. So that acceleration is always constant. That's one example of such cases. So in this case, we have the same thing. Now we need to find what is that constant acceleration value. That's what 6.4.2 is all about. So we are given the displacement, right? And we are given the VI. We are told that it starts from rest. So if you remember, whenever we are hinted that there's constant acceleration, it means you can use your equations of motion to find whatever you need to find. So here we have VI and then we have this, but we need to find, we also have VF at Y because they said acceleration of the car. So yeah, we have VF at Y. So we can find acceleration by saying VF squared right, this one formula. It's in your formula sheet as well, so you can go through all of them and then you check which parameters do I, or which physical quantities do I have. You use the formula that will only leave you with one unknown. If you check, I have my VF, which is the velocity at Y. I'm looking at this thing from X to Y, remember? So my VF is at Y, which is my last point in the trip. My VI is at X, which is where I starts. That's the initial velocity, VI. VF is the final velocity. I also have my delta X, which is my displacement, this guy. Right, I have all of these things. All right, so I'm only left with one unknown, which is my acceleration. So I can use this equation. This is how we evaluate which equation to use. If you check the other ones and you see that you would need to calculate something before you get to solve, then you can avoid those ones. Sometimes you can't really avoid it, especially if this was like a 6-mark question, then you would understand that, oh, okay, it means that I can use two equations because Even the mark allocation warrants it. So 6.4.1, we can say Vf squared is 2Vi squared plus 2A delta x. Vf, we just found it to be 30.51. Vi is 0 squared plus 2 times A times 80, what was this distance? 83.11 meters. Then you can solve for A. Just divide both sides by 83.11 times 2. So it's 30.51 squared. All of that divided by 2 times 83.11. So I get 5.60 meters per square second. Okay, so that's our acceleration. It's 3 marks, and that's how you find it. How did I know to use the equation of motion? They told me that this thing is accelerating constantly. So equations of motion are only usable if you are dealing with constant acceleration. Always remember that. If the acceleration is not constant, you can't really rely on those equations. You have to use other means. All right, so now let's go to 6.5. A study of spectral lines. Okay, a study of spectral lines obtained from various stars can provide valuable information about the movement of the stars. Okay, yes. So the two diagrams below represent different spectral lines of an element. Diagram 1 represents the spectrum of the element in a lab on Earth, and then diagram 2 represents the spectrum of the same element from a distant star. So this one was taken from a lab, and this one is when they observe a distant star. Let's call it star. So the question now comes, is the star moving towards or away from the Earth? Explain the answer by referring to the shifts in the spectral lines. Okay, so the rule is if the spectral lines shift towards the red end, I'm talking about the spectral lines of the star, because remember we have a control, which is the one we took at the lab, right? And now we are observing a star. So the rule is if the spectral lines are shifting towards the red end, so if they were shifting towards this side, the red end, towards the red end, it would mean the wavelength is increasing, frequency is decreasing, and the star is thus moving away from the Earth. This is called a redshift. Okay, but on the other hand, if the spectral lines they shift towards the blue, or usually sometimes it can be violet, right, it means the wavelength is decreasing and then the frequency is increasing. Then the star has to be moving towards the Earth. This is called a blue shift, right? So that's what happens. So from the diagram we can see that the spectral lines are shifted towards the blue end. If you can check, they are shifting more towards the blue end. They are going this side, right? The ones that we observed for the star. And since they are shifting towards the blue end, they indicate a decrease in wavelength. Excuse me. They indicate a decrease in wavelength. Therefore, the star is moving towards the Earth. Yes, that's how you do the red shift, blue shift, right? So these are all due to the Doppler effect, right? Remember, if something is moving towards you, the frequency of the wave fronts increases. As the frequency increases, it effectively reduces the wavelength. So it means that thing is moving towards you. Yes, that's another way to check if the stars are moving towards or away from the Earth. So that's your answer. So we would say the spectral lines, or we must first choose the answer, which was choose between, is it moving towards or away? So we'll say towards the Earth. The Earth, and then why is it moving towards the Earth? Now you must explain. The spectral lines are shifted towards the blue end of the spectrum. This is called a blue shift. Alright, so this is exactly how you would go about it. So we know that it's moving towards the Earth. Why? Because the spectral lines are showing that they are shifting towards the blue end of the spectrum. So if they are shifting towards the blue end of the spectrum, this is indicating a decrease in wavelength. And an increase in frequency due to the Doppler effect. Remember, the Doppler effect says that if the source suddenly moves, or either the source or the listener, if one of them are moving towards the other, what happens is the wavefronts, the rate or the frequency of the wavefronts, the observed wavefronts, increases, thereby reducing the wavelength, and as a result, in this case, it means that this thing would be moving towards the Earth, right? If it was moving away, the opposite would happen. So that's how the red shift, blue shift, I even put it in brackets for you here. This is just a blue shift. When the when the spectral lines are shifted towards the blue end, right? And then it's called a blue shift. When they're shifted towards the red end, it's called a red shift. All right, that's it for question 6. Let's go and check question 7. Coulomb's law. All right. So this is Coulomb's law. Sphere P with a charge of minus 30 coulombs is placed on an isolated stand. Sphere Q. So there's a reason they isolate the stand, is so that we reduce the leakage of the charges. To eliminate it, actually, not even reduce, eliminate it. So sphere Q with charge minus 20 coulombs hangs on an inextensible string from a horizontal beam and is at a distance of 80 centimeters from sphere P, as shown in the diagram below. Okay, nice. State Coulomb's law in words, right? Remember what Coulomb's law says? It says, well, when two charged particles are placed next to one another, what question is that? That was 7.1. They will exert an electrostatic force on each other. Now, the magnitude of the electrostatic force will be directly proportional to the product of their charges, but inversely proportional to the square of the distance between them. So when I write this formula, which is Coulomb's law, I usually remember what the law says, because that's literally the law but in formula form. Okay, if it can help you remember as well, always write it on a separate piece of paper and then just explain the formula, but basically in words. That's what you're doing when you are stating a law but in words. That's what you're doing. You're taking the formula and you're just explaining it in words. All right, so that's what it says, Coulomb's law. So let's write it. Right, so it says the magnitude so it's the magnitude of Okay, let's write it, of the electrostatic. So Coulomb's law is typically for point charges. So even in the definition, you'll find that you're talking about point charges. So yes, I just wrote it out for you. So the magnitude of the electrostatic force exerted by a point charge on another point charge is directly proportional. So when they say a point charge, we're talking about would be your Q1 or Q2 on another point charge. Now that's your Q2 is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance. That would be your R squared between them. Okay, that's what the law basically says. Draw a labeled free body diagram for sphere P. Okay, let's check out sphere P on the diagram before we draw a free body diagram. So sphere P, there'll be a tension because there's a string here. Remember when we read there was a string there? So there'll be tension there. And then it will experience an electrostatic force due to the presence of Q. So this will be a repulsive force. That will be FQ on P. Okay. And then what else do we know about this one? Distance. Right, so for sphere P, it's only those two forces. I'm not sure why this is 3 marks. So, but for sphere Q, you would have the tension. You'd have, or if there was weight, then it would be 3 marks perhaps. Weight of the sphere, but we were told nothing about the weight, so nonetheless we'll only get 2 forces there. So we can draw it as 7.2. Oops, my dots is not dotting there. So now you get the tension, and then you get the repulsive force. Electrostatic force, which is FQ on P. Alright. So that's our electrostatic force. You can even call it just F. It's up to you. I'm labeling it like this so that I know. So now, for 7.3.1, first, just before we move, let's make sure we have all our forces. Yeah, the only force that's missing is weight, but since we're not told about the masses of the spheres, we'll assume that the weight is negligible. But the third force would have been weight. Okay, third force would have been weight, but they didn't mention anything about mass, so I'll assume it's negligible. So electrostatic force between the two spheres, we have to calculate the magnitude of the electrostatic force between the two spheres. Okay, that's F. In fact, let's just call it F. Wow, I think it was fine. FQ on P, there's nothing wrong. Okay, K Q1 times Q2 over R squared is how you do the electrostatic force. K is a constant, 9 times 10 to the power 9. We are told that Q1, which is, I'll make Q1 my P, that's 30 microcoulomb. We know that micro is 1 times 10 to the power minus 6. Pico, nano is 1 times 10 to the power minus 9. And picocoulomb is 1 times 10 minus 12, right? Something like that. And then, so since this is micro, we'll do 30 minus 6. Okay. If it was micro, it would be minus 3, something like that. All right, so Q2 will be our charge Q, which is 20 microcoulombs as well. So some people, they just do this. They say 30 times 20, and they multiply all of this times 1 to the power minus 6, basically. You can do that as well. but I prefer just doing it one by one, so that in case the charges are not of the same magnitude, I could always pick it up. You do that if the charges have the same magnitude, like they are both microcoulombs in this case. And we are told that the distance between both of them is 80 centimeters. 80 divided by 100 is 0.8. So we square that. So we're dividing it by 100 because we are converting from centimeters to meters. We only work with meters here, remember that. This is 30 minus 6 times 20. We don't include the signs for the charges when we're calculating the force. It's not important. 0.44. This is what I get, newtons. Okay. 0.44 newtons. That's our electrostatic force. Now we are tasked with finding the tension T in the string if the mass of the sphere is 90 grams. Okay, so you see what I mean? Perhaps since it's 3 marks, let's include the weight of the sphere here. But it's good to, they should have specified that the spheres have a mass m or something like that, so that we would be sure to include the weight component. Since they didn't specify, it was a mission. But that 3 marks, like I said before, it means you must have 3 forces. So we had 2. Let's add weights. That's our third force. Alright, so 7.3.2, we are just finding the tension in the string if the mass of the sphere is 90 grams. So because this thing is in equilibrium, right, you can even draw a triangle. So what will happen is Q, it will be like this. If we draw the free body for Q, you can make it this is T, this is weight, and then that's the F. So if you remember the closed vector diagram, so you would have T there, you draw the vectors as they are, you would have weights going there, right? Since this thing is in equilibrium, we can draw it in a closed vector format. It's not moving. Okay, my attention. If you check, I haven't changed the nature of the vectors. T is still a diagonal vector or a 2D vector. Weight is still just going down. And then I have my force, electrostatic force, due to the repulsion from P. I will call that F. And then what happens is, that's what I get. It will be a right angle triangle. Now, if the theta will also be there, okay, between T and P. That's our theta. Okay, so we are not told what theta is, right? So now what we do know is we know F. We can find weight and thereby find tension using what's this thing? Using Pythagoras theorem. Okay, so that's what we can do. So like I said, you have weight, you have your tension vector, which is T, you have F, then that's your theta there. So we can comfortably use this diagram. This is called a closed vector diagram. It's only for objects or systems that are in equilibrium. If you remember the first topic in grade 11, which is vectors, you had to draw something like this for special cases where the things are in equilibrium, where the object is in equilibrium. So we can also use it here to find our tension in the string. So we have F here. So if you know what I'm talking about, what we're saying is we already know weights. We can find weights to be, in fact, let's do it underneath here. Okay, it won't fit. So you're not allowed to divide your page like this, né? But what I'm doing is to make sure that everything stays in this page. I'm dreading the whole process of starting a new page when I can make everything fit here. I can force it actually. So weight is mg. We are told that the mass is 90 grams. That's 90 divided by 1,000. So that's 0.09. I think, let's check. 90 divided by 1,000. Yes, it's 0.09 times the gravitational acceleration. And then what we get is 0.882 newtons. That's my weight, okay? I leave it there. Now, I have my force, which is F, this F. So what I can do, I can use Pythagoras theorem. I can say therefore T squared is equals to F squared plus W squared. Remember, this is A, this is B, this is C. So we're basically saying Pythagoras theorem says, let me change the color of these so that they can stick out. If this is my side A, my side B, and this is my side C, because remember, this is just a triangle, a right angle triangle. I know I didn't indicate that on this one, but on the previous diagram I did, okay? So what we're saying is, I can say that C squared is basically equals to A squared plus B squared, okay? And in this case, C is T, or I flipped it. Let me do it according to those letters there. This is my C, this is my A, this is my B. So that's ABC. So C is my T, that's my hypotenuse side. A is my B, is my F, that's my adjacent side. And then B is my weight, that is my perpendicular side. So from here, I can simply say therefore T. That's one way, by the way. Another way, you could have easily used equilibrium. T is equals to, I'll show you the other way for those that understand equilibrium to that extent, or that I understand another method. We know that F, we found it to be 8.44. This will be a very small difference. We could have just said this thing is just 8.44 plus 0.882. This 0.882 will cause a very small difference. Alright, so 8.44 squared plus 0.882. It just causes a difference of 0.04. I get 8.49 newtons. So that's my tension. Alright, so another method that you could have used, I'll write it quickly here. You know that T will have components, right? That's another method. You'll get a T. Let me use my original colors. You'll get a Tx, the x component of T. Then you'll get a Ty, the y component of T. And then of course, our weight is there. So what I'm saying is, then our theta will be, it's always between the perpendicular component and the hypotenuse, yes. So that's theta there. Now, here's what I'm saying. I'm saying you can use equilibrium, but then you would need theta, which we can only find theta at this point, okay? But if theta was given, you could have said that your weight will be equals to Ty. That's it. Since you can find your weight, you would say something like, okay, Ty is equals to Ty, which is T cos theta, right? But you would use this method if you knew theta, because from here you can simply say T is the weight divided by cos theta. Then that's your answer. right? That's how you would do it. Or you can use Tx, whichever way, right? Because you already knew F. You can use whichever way will be quicker for you. You can say Tx is equals to F, because this thing is in equilibrium. It means forces are balanced in every angle, in every direction. So along the x-axis, forces are equal. Along the y-axis, forces are equal. So I'm equating the Tx with the F, because that's along the x-axis. I'm equating the Ty with the W with the weight, because that's along the y-axis, right? So yes, that's equilibrium for you. You can do stuff like that. But since we don't know theta, it's fine. I think we can use it for 7.3.3, okay? So 7.3.3. Okay, before we get there, see if we can. Alright, so now we are required to find the angle theta. I'll write everything here for theta. So for theta, I can simply say Tx is equals to, like I was saying, F, right? Or I can say, actually, I don't even need to do that. I can come to my triangle here and I say tan theta. I can say tan theta is equals to opposite, which is F, over opposite over adjacent. And then my theta would simply be tan like that, F over W. And then from there, my F was 8.44. And then my weight, what did I find weight to be? 0.882. That's a weird weight. So what do I find here? 8.44. I get a theta of, it's a very big theta. We must check it out. Let's see, 0.3. Oh yes, it's fine. 0.3, yeah. Degrees. All right, so that's our answer for theta. It's quite a big theta. It's very suspicious, but let's just double check. In principle, yeah, we did everything fine, so it should be fine. Paste. All right, so this is how we would find, this is how we would answer question 7. I think that was the end of it. You can also use Tx and say, like what I was showing you, Ty is equals to W. You can find theta using this, or you can find theta using that. The theta you would find would likely be a bit lesser than mine. You might maybe find here that your theta will be 80. Let's say I found 83, right? What did I find? Found 84.07. You might find that maybe find 83.99, something like this, okay? So it's just because the method you're using, and also rounding differences, they matter as well. But more or less, the answers shouldn't be far off from each other, okay? You can try using these two methods and check what theta you find and compare to the one that I found using tan theta, okay? All right, so why did I use tan theta? I came to this angle right here. I know that theta is here. Usually when we find theta, we use tan. So I just took that. I said opposite, my opposite side over my adjacent side. Then I found theta like that. So that's where I got tan from, just from my right angle triangle that we constructed using the method of closed vector, a closed vector diagram. So there's now question 8. It's still on, this is the second last question. It's still on small sphere, on electrostatics. Okay. Now, so for this one, we have what? Two small spheres, A with a charge of 5 nanocoulombs. Remember, nanocoulombs is -9, and B with a charge of -4 nanocoulomb. They are placed a certain distance from each other in a vacuum, as shown in the diagram below. Okay, that's all we are told. We are not told the distance between them. So let's call this distance x. We don't know it. Or it's r actually. We don't know what r is. So let's call it just r. All right, so 8.1, we are required to define the term electric field in words. Remember, electric field, it's just, also you must be very careful. There's what you call electric field. Then there's what you call, there are two of these definitions. Electric field strength at a point, or yes, there's those two definitions. So now electric field is just a region of space in which an electric charge experiences a force. It's just a space. So you would find this on your notes, or some people, they get it from exam guidelines. I think exam guidelines usually list all of them. So if you check an exam guideline, you will find all of these definitions. So electric field, we simply say it's just a region of space in which an electric charge experiences a force. All right, so that's how we would state that one. Now let's go to 8.2. What's on 8.2? Draw the electric field pattern between the spheres A and B. Oh yes, so this one you must know. So you have sphere A here, and then you have sphere B. So we want the same size. I just like it when it's the same size. So one is, I think, which one is positive? One is positive, which is A, and the other one is negative, which is B. So remember now, if one is positive and the other one is negative, you will get field lines that are moving from one sphere and connecting to the other. The field pattern would look like that. One sphere to the other, one sphere to the other. All right, let's say I draw maybe 3 of these. Okay, so these must not touch and they must not cross the circle. So what I did there is a bit wrong. They must not cross my circle there. Oh no. Okay, that's fine. All right, so that's our sphere, our pattern. And then remember, we are moving from positive towards the negative always. So the arrows are pointing towards the negative. Even here, when you draw these lines, these ones, okay, they look ugly. Oops. They must connect. They must be symmetrical. If I have 3 lines at the top, I must have 3 lines at the bottom, like I did here. And then now, oh yes, I can draw as many lines as possible actually. Right, they are going out, going out, going out, going out. Here we do the same thing. Let me draw 2 as well here. So these are going in, going in, going in, going in. So this is how you would draw the field lines. Okay, first of all, they must not touch. Secondly, it must be the correct thing. All right, so that's it. You must just, this is what you must always keep in mind when drawing these things. So 8.3, X is a point left of spheres A and B. Okay, point X is at a distance r from sphere A, and sphere A is at a distance 3r from sphere B. So as shown in the diagram below. Okay, the net electric field at point X is that one, 4128 west. Okay, now calculate the value of R. The value of what? R. So let's try to find what is the electric field at a point X due to A. Okay, let's start there. And then we will find the electric field at point X due to B now. Okay, then from there, because this electric field, it's the net electric field experienced at point X. So if we calculate the individual contributions of this charge A to the electric field at point X, to the net electric field at point X, and we come again and calculate the contribution of sphere B to the electric field or the net electric field at point X, we will then be able to relate it with this value and hopefully solve for our R. Okay, what do I mean by that? Let's do it. I can say okay, I'll even let's say 8.3. I'll start here. Electric field at point X, right? Due to A, due to the charge A. Remember, point X is our reference point. So what we are doing here, we are saying, okay, I'm standing at point X. I'm standing here at point X. And then I see these two charges. So the amount of electric field that I will feel at point X will be due to the individual contribution of these charges A and B. So that is the net that I will feel, which is this guy. Okay, so the net can either be greater than the individual contributions, especially if both charges are contributing in the same direction, or it can be lower, especially if the charges are in opposite directions, but we will see. Okay, so we always assume that at point X there is a positive test charge, so that we can decide the direction of each electric field, of the direction of the electric field produced by each sphere. So if I put a positive test charge here, sphere A, because it's positive, what will happen is it will cause this thing to go that way, to repel to the left. So we can say the direction of the electric field at X due to A is to the left. Or they used west here. Okay, it's to the west, yes. Right, A contributes to the west, while B, because B is negative, this test charge will be attracted to B, so it would want to move towards B. So B has a contribution to the east instead. So what that does, it introduces a new dynamic. What we want to do now is we need to choose a direction that we consider positive. So I will choose the direction west as my positive, because it is the direction of my net electric field at that point. So it's easy to deal with that. So anything that is opposite west will be negative. So B will have a negative electric field because it's going to the east. I'll show you in the calculations. Let's go through it. So let's start with the electric field at point X due to A. Okay, we know that it's equal to E, let's call it E1 KQ1 over R squared, right? That is 9 times 10 to the power 9 Q1 is, we're told it's 5 nanocoulombs, I believe. That's 5 times 10 to the power minus 9 over r squared. This will give us, so the reason I'm substituting r is because we are told that the distance is just r, okay? Now we'll say 9 in 9 times 5. Okay, so this is 45, which makes sense, over r squared, because if you check this and that will take each other to 0, so you'll just have 9 times 5 multiplying each other. All right, so 45 over r squared, that's my first E1. Now I take the same thing, but due to B now, you must pay attention to this one. Now I want the electric field at point X due to B. So I put B here. So what is that? I'll say E2 is now KQ2 over r squared. That's 9 times 10 to the power 9. What's the charge on B? And how far is B from X? The charge on B is 4 nanocoulombs, minus 4. The charge on X, the distance from X is 3 plus this r, so it's 4r. So we must keep that in mind. We said this is 4 times 10 minus 9 over the distance is r plus 3r, all of this squared. So this is 4r squared, okay? You can do it like that. So let me just write it here. It's 9 times 10, so that's, you are clear, over 4r squared. All right, so that's what we're doing now. So I get 4, this is 16, but it's fine, let's do 4 squared. I get 2.25 over r squared, okay? That's what I get. Right, so now let's find the nets then. We know that E net would be E1 plus E2. Must be careful now. Let's do it. But E2 is to the west, so it must be minus E2. So this is west. So before we obviously make it a negative, let's make it clear that we chose east. Oh no, this is to the east, sorry. This is to the east. E2 is the electric field at point X due to B. And we said that B will pull a positive test charge that we put at X towards the east. So since we're choosing west as positive, when we substitute the electric field contribution for B, we will make it negative because it's going to the east. So we must state it here that we are choosing west is positive. Why do we do this? So that we don't just substitute negatives and positive without a clear reason. Now we can go ahead and substitute, okay? We have 4128 for the net electric charge. That's 4128. And for E1 is to the west, so we are fine with E1. 45 over r squared minus 2.25 over r squared. Okay, good. So now we can solve for r. It's just maths at this point. I know I've said that a lot, but it's actually true. At this point, it's simply maths. There's nothing more to it, really. So don't get tired of me saying that. It's just maths at this point. At some point, it stops being about physics. It's about how good are you with your maths. So here, obviously, the common denominator is r squared. So your life is very simple here. If I want to take it step by step, I can say common denominator is this one, 45 minus 2.25. It's as simple as doing that. Then my r will just be a square root of 45 minus 2.25 is what? I don't want to take it elsewhere. I want to finish it off here. So this is square root. What is 45 minus 2.25? It's 42.75. All of this over 4, 1. Alright, so that's how we would find our thing. Good. Not our thing, sorry, our r, our distance from, which is 0.10 meters, okay? Very important. That's our answer. If you leave out units, your answer is incomplete. Therefore, you must get a 0. Okay, that's in my books though. But other than that, you will get incomplete or missing marks, if that makes sense. Okay, now everything fits perfectly. All right, so this is how we would do question 8. I hope you are with me so far. I know this video is very lengthy, but we have to finish. This is part 2. Part 2 has to end, okay? Otherwise, we will have a part 3. If you want to have a part 3, it's fine. You can pause and then come back another day and finish off, okay? So, yeah, let's continue. Ooh. Last but not least, we are with question 9. Electric circuits or electricity, depends on. Yes, so now let's check this one out. Okay, in the circuit diagram below, the battery has an EMF of 10 volts. Okay, that's EMF, so our epsilon. Right, and an unknown internal resistance R. Okay, voltmeter V1, where's my voltmeter V1? Is connected across an open switch, and V2 is connected across the battery. The resistance of the connecting wires in the ammeter can be ignored, okay? That's fine. Switch S is open. So the only thing we are given here on the statement is that our EMF is 10. Okay, so since now this battery has an internal resistance, it means V2 will not be equal to 10 volts, because some of the voltage, which is energy, will be used up to overcome the internal resistance of the battery. Thereby, the voltage or the potential difference that is measured by V2 will be lower than that of the battery's EMF. You'll find that maybe it's 9 or 9.8 or something like that. Depends on how big the internal resistance of the battery is, okay? All right, so that's what usually happens. Now let's continue. Remember what I always say, start by tracing your current. So if you check, current will live, it always lives on the longest wire, which is this guy, the longest line on our cell or battery. So it will leave this side as total current, let's call it I. It gets here, it says that, oh, okay, this is a parallel combination. So let's divide. I will split myself. I will have I1 going there. Now I'll have I2 going to branch 2. So branch 1 receives current 1, branch 2 receives current 2. Then again, it will meet here and continue as I total. Okay? Alright, so if this thing is closed like this, the current will continue. So that means our 1 ohm resistor receives total current, and then it passes here, passes there. It means our ammeter as well reads a total current, okay? So that's it. That's it for, it's very important to trace the current, because you see now I'm already answering some of the questions that I might encounter in the question once I start reading. All right. Now let's add a page and start answering questions now. All right, so first off, we are off to a start. We are, as stating Ohm's law, right? So 9.1. So Ohm's law, remember, it simply states that, well, the potential difference across a conductor should be directly proportional, or is directly proportional to current. Of course, there's a condition, so provided that the temperature remains the same or remains constant, depends which one you prefer using. So that's what not Coulomb's law, Ohm's law states. Okay. So yeah, we'll say that the potential difference all right, so that the potential difference across a conductor is directly proportional to the current flowing through it. Of course, provided that the temperature remains constant. Usually it's the temperature and other factors, but for grade 12, we just focus on temperature. All right, so 9.1.1. What is the reading on voltmeter V1? Ooh, this is an interesting one. So remember, switch S is open. So let me remove my current for now, because switch S is open, so current won't really flow like what I did unless they close switch S. But you have the brief idea of how it would flow if switch S closed. So when, let me not forget about the current for now, right? Just know that switch S is opened. Don't mind the current. There's no current flowing because switch S is open, okay? So no current will be flowing in the system until switch S is closed. So everything we were tracing, remember what I said, if switch S is closed, everything we traced will occur. It will happen in that fashion. But now it's open and we are being asked, what is the reading on voltmeter V1? This is an interesting question because this switch is open. So if this switch is open, what normally happens is, since there is no current flowing, because the switch is open, V1 will measure the EMF. Let me repeat. Since the switch is open and there's no current flowing, V1 will measure the EMF. But how does it work? Remember, for potential difference to exist, there must be a potential drop, which means when I compare point A, which is before and after the switch, of course, in this case, I say this was point A, then this is point B. There must be a potential drop because current is flowing there. So no current will be flowing through the resistors. No current will be flowing between the switch and so on, and throughout the whole wires, basically. So we just have voltage sitting there in the battery, nothing happening to it, okay, the EMF. So as a result, remember we said EMF is equals to the V lost. We usually say I, right, something like this. Excuse me. What's that formula again? VE is V lost. I want this one plus the external X. Let's just say X. Right. So that's what we usually use. Okay. So now, because there's no current flowing, the voltage that will be measured by V1 is simply the one on the battery. Because on this side, if you check the battery, okay, what have I done is it has, we said what, an EMF of 10 volts, right? Now, so the philosophy is, if current is not passing through the circuits due to the open switch, of course, what ends up happening is the voltage across every resistor will be zero. Why? Because remember, V is I times R. So if there's no current, you'll get 0 times the resistance, which is 3 or 6 or 1, ohm, you still get 0 volts. Okay, so if you get 0 volts, it means the 6 ohm resistor is 0 volts, the 3 ohm resistor 0 volts, the voltage across the 1 ohm resistor is also 0 volts. So no current means there won't be any voltage drops in the external circuits. So now the battery is still trying to push charges around the circuit, but the open switch is blocking the path. Okay, so then of course, as a result of this, the entire battery voltage will appear across the gap here. It's like you'll have 0 here and 10 there. So remember, the potential difference between A and B will simply be just 10 volts. So whenever you have an open switch and you try put a voltage across that and you want to measure the voltage of the circuit, it will simply give you the EMF of the battery, which is not a true reflection of the total external voltage of the circuit. Okay, so that's what happened. So now all of this pressure, all of this voltage, all of this potential difference will just be at the open switch. So that's why you get 10 volts being the reading on V1. Okay, so another way to sort of think about it is if you think about it as water behind like a closed valve, or not a valve, behind a wall. Say you have a wall here, then there's just water here, right? What happens is the entire force of the water will be concentrated at the wall because it's trying to push through the wall, right? As a result, all of the pressure will be there. Now, so what happens is the same thing that happens there is what happens here. So the entire battery voltage, or the entire battery, the battery is trying to push energy across this bridge here, but there's no path, okay, for current to flow. So what ends up happening, you get the entire potential difference being concentrated at the open switch. That's why the voltage at V1, when this switch S is open, will be 10 volts. So it's always basically like that. If you try to measure the voltage when there's an open switch and you put that voltmeter at that switch, you will get simply the EMF of the battery or of your power supply in the circuit. Okay, so yes, so here it will simply get V1 being 10 volts, which is the EMF. Okay, it's just the potential difference across the switch. All right, so you have basically voltage coming. Remember we said current would be leaving from this side. Imagine voltage coming all the way. When it reaches here, just imagine that it's still 10 volts because it hasn't been dropping. It was not dropping. It didn't drop at the 3 ohm resistor. It didn't drop at the 6 ohm resistor. There wasn't a potential drop. So it gets to A. It can't pass through to B. So that means at B you have 0 volts, but at A you have 10. So the potential difference now becomes 10. Because remember, that's what a voltmeter measures, or that's what voltage is. It's a potential difference. Okay, so that's basically the logic. All right, now we have 9.1.1. is it 9. Oh, they made a mistake here. It should be 9.2.1 and 9.2.2. okay, 9.2.1 V1 will be 10 volts, and then 9.2.3, now we're being asked about V2. So V2 would usually measure the potential the potential difference across the battery. So then what happens now is, since the switch is still, it's still opened, there won't be current passing through, right? So V2 tends to measure the external voltage. right? But since there's no current flowing, it can't really measure the external voltage accurately. So it'll still behave like V1. It'll just simply measure the EMF of the battery. Same explanation as V1, right? You have a voltage of 10 volts, but on the other hand, there's just 0 volts. So the potential difference is simply 10 volts, right? That's what happens. So that's what would happen to V2. So it still measures 10 volts. But this is when the switch is open. Once it's closed, do not rely on V1 and V2 measuring 10 volts, okay? They will measure something different. So let's continue. Okay, so you see, switch S is now closed, which is when we continue. Reading on V2 drops by 2.5 volts. Okay, so it means, remember we said V2 when the switch was opened, it was measuring 10 volts. But now when we close the switch, that voltage will drop by 2.5. It means V2 now measures, so let's go to 9.3. It means V2 is now equals to 10 minus the drop, which is 7.5 volts. That's the voltage measured by V2. Remember, this voltage is the voltage of the external circuit now. It's this voltage, this one. Why is it dropping? Because once we close the switch, current starts flowing. Then we get voltage drops across the whole circuit. The first voltage drop is at the battery. Due to the internal resistance, there will be a voltage drop there, right? So that's why this V2 will stop measuring EMF and start measuring the actual voltage drop across that battery, which is 7.5. I mean, the potential drop, not voltage drop, the potential drop, which is 7.5 volts. Okay, so that's what happens there. So that's what happens. That's the first thing we would note for 9.3. So let's start answering 9.3.1. Calculate the reading on V2. Where's V2? Oh, it's 1 mark. It's what we just did there. So I can call this 9.3.1 then. And I call this 9.3.2. What is the reading on the ammeter A? Okay. On the ammeter A. So what we can do, we can use our famous formula. E is equals to V lost plus V external. But it won't be useful to us when it's like this, because we will try to calculate the current. So we know that we can use it in this form. I, total current. Remember we said A reads the total current when the switch is closed. And then R, which is the total resistance of the circuit, the external circuit, plus the internal resistance of the battery. That looks like a V, but it's actually an R. Much better. All right, so now we need to find R, the big R. We have a series and a parallel combination. This is a parallel, this is a series. So let's go ahead. We can say R is equals to RP plus RS. RT, let's call it RT, which is the total resistance. RP, since we have two resistors in parallel, we can use this one, R1 times R2 over R1 plus R2, okay, plus RS. So if you know that you'll forget this formula, you can use that one that says 1 over R1 plus 1 over R2, and then you invert this, of course. You don't leave it as it is. Then that's your RP, okay? Yeah, that's still fine. You will get the same answer. We are taking a shortcut because we know whenever you have two resistors only, you can use this formula. But once you have 3, 4, and so on, you can't use this formula here for resistors in parallel. All right, so R1, we found that R1 is 3 ohms and R2 is 6 ohms. So this is 3 times 6 over 3 plus 6 and plus the series resistor is just 1 ohm. So that's what we get. So this is 18 divided by 9 plus 2 plus 1. That should be 3 ohms. Let's just confirm. 3 times 6 over 3 plus 6. Okay, yeah, it is 3 ohms. Okay. Let us continue. I don't like this ohm. It can be nicer. So now we want to find the reading on the ammeter. Okay, we have the total resistance now and we know the EMF. We can go ahead and find it. So E is simply the total current, the total resistance plus the internal resistance. We know this is 10. Total current is what we're looking for. This big R is 3, which is what we just calculated. This guy, that's that. And then plus our R is, what's our internal resistance? Or do we still need to find it? Okay, we can do it like this. It's not an issue. We don't need to find it. We can say it's not an issue. V lost, we have to plus Vext, right? What we can do, since we don't know R, but we know the loss voltage is 2.5, right? That's for V2. Remember, they told us V2, the voltage drops by 2.5. So that is 2.5 is the lost voltage. We are sure about that. This one, right? So V lost plus I times R. Okay, so we can do that. We know Vext, but let's just use I times R. And then now we have 10 here. So we have 10 minus 2.5 is 7.5 is equals to I times R is 3I. So I is 7.5 divided by 3. I think you'll get 2.5 amps. Yes, divided by 3. Yes, 2.5 amps. Of course, you didn't have to use this formula. Alternatively, what you could have done was say, I know that the total current is simply the total voltage divided by the total resistance. Our total voltage is 7.5 over our total resistance is 3, and you're going to simply get 2.5 amps. So it's this, or that's a big or here. It's up to you which one you use. So yes, so that's one thing you could have done here. So calculate the internal resistance of the battery. We know that for 9.3.3 V lost is IR, I times small r. So we know that our loss voltage is 2.5. Our I, we just found it to be 2.5. And then now R. So R is simply 1 then, 1 ohm. Okay. R is simply 1 ohm. That's a very big R. Very, very big internal resistance for a battery. But shouldn't be too bad. Alright, so how will the voltmeter reading V2 be if the 3 ohm resistor burnt out while the switch is still closed? Okay. Write down increases, decreases, or remains the same. Alright, so let's think about it. If we burn out the 3 ohm resistor, what we've effectively done, we create an open circuit here because current won't be able, it's like we create an open switch here where there was the 3 ohm resistor. We create like an open switch. So current won't be able to pass in that branch anymore. So what that does is it removes this branch. It removes that branch entirely. So what we end up having is a parallel circuit with 2 resistors. A 6 ohm resistor, no, not a parallel circuit, a series circuit with 2 resistors, a 6 ohm resistor and a 1 ohm resistor. So we end up having something like that, okay? So once you have that, ultimately the resistance of the circuit increases. So if the resistance of the circuit increases, what happens to the voltage? We know that V is equals to IR. So the higher the resistance, the higher the voltage, according to Ohm's law. So if the resistance of the circuit increases, the voltage will also increase. So therefore V2 will definitely increase. You can even plug these values, you will see. You'll find that the voltage will increase. What do I mean by plug the values? So remember, once resistor 3 ohm burns out, you will have a new circuit. How will your new circuit look like? Let's try and draw it here. The new circuit will have your battery there. It will have your ammeter there, your ammeter. It will have your 1 ohm resistor there. And your switch there. Your switch is still closed, as they said in the instruction. Your 6 ohm there. That resistor looks weird, but it's a 6 ohm resistor anyway. So this is your new circuit. So check this. The new circuit is completely what's this? Oh, let's put V1 there, it's fine. V2, sorry. The new circuit is completely series connection. There's no parallel combination. So if you check, the new resistance will be R is equal to 6 plus 1, which is 7 ohms, right? If it's 7 ohms and our old one was 3 ohms, you can tell that it has increased. The difference between 7 and 3 is like 4 ohms. So there's been an increase of 4 ohms when that one burns out. So if I increase the resistance, my voltage has to increase there at V2. Okay, so that's the logic. Here you just use Ohm's law to answer this question. So let me write down what you could have said. Is it what? 9.4, okay? Let's do it. 9.4. When 3 ohm resistor burns out, this is going to be a long paragraph, but you will get the idea. It becomes an open circuit. So the total external resistance becomes resistance becomes what? Oh, not becomes, sorry, it increases. Increases. Why? Because now the circuit is a series circuit instead of being a parallel circuit. So the total external, I wrote total twice, that's weird. The total external resistance increases, right? The current supplied by the battery decreases. Excuse me. So let's write that the current, why is it decreasing the current supplied by the battery? Because the resistance has increased. The current supplied by the battery decreases. Reducing the loss volts, okay? So this will reduce the voltage that we lose, because remember, loss volts is their I times R, okay? But I'll write it for you. Right, reducing the loss volts, which is I times R, across the internal resistance. Writing and speaking is very hard. Writing and speaking at the same time. Across, I'm using saying there. what am I saying, across the internal, yeah, let me say it like that, internal resistance. Right, now I'm concluding. Okay, so since the EMF is equals to, not the EMF, the external voltage, Vext, you take the EMF minus the lost volts, right? Therefore, that's what I'm saying. Therefore, if we drop the lost volts, we will effectively increase the external resistance. Therefore, the reading on V2 increases. So the reading on V2 is simply the terminal potential difference, or the external, the Vext. Some people call it the terminal potential difference. I know this looks like a long paragraph, but I know it will make you understand what I'm saying. Alright, so this is what will happen. So whenever you are faced with circuits where the internal resistance is not negligible, and they ask you a similar question like this, the answer is pretty much always this one. So even if they were reducing the resistance instead of increasing it, you would say the opposite, but using the same template I just laid out here. Okay, so yeah, that's what you would typically do. Right. So this brings us to the end of our of our pre-exam. All right, so the walkthrough was that. I hope you got value off of this, and yes, all the best for those that are writing, who will be watching this video, before the exams. All right, I'll catch you on the next one. Cheers.